All right, so we can start now. I'm recording, so go ahead.
Okay, well, some of my questions are kind of simple, I think, but for the double nucleophilic acyl substitution,
Yep.
with the LAH reduction method,
Yep.
is the mechanism like the way the double bond attacks, like, is it the same as it was with what we just did?
Yeah, so let's say we want to reduce this, and we use LAH as in our first step, and then we use 15% sodium hydroxide to work it up. Sorry, I knew I was about to sneeze. So what you get out of this reaction is actually 2 molecules of ethanol. One molecule of ethanol is going to come from here. The other molecule of ethanol is going to come from here. Okay, so how does that work? Well, the first thing that's going to happen is we're going to get a nucleophilic acyl substitution. And so we have aluminum hydride, looks like this. Okay, the aluminum hydride sigma bond attacks the pi star CO. Electrons move up onto oxygen as a lone pair. So we've got a new carbon-hydrogen bond. O ethyl's still there. We've got O minus, and if you wanted to say that the oxygen was actually attached to the aluminum, we would have like that. Okay, then we get collapse with loss of a leaving group. And in this case, the ethanol is just going to attack the hydride. The ethanol is going to attack the aluminum, excuse me. And then you'll still have an equivalent of hydride available. Okay, so like this. And so that's going to perform not a nucleophilic acyl substitution, but now a nucleophilic addition, right? Attack of the carbonyl. So you now form another CH bond, O, aluminum, H, O, ethyl. Aluminum's still negatively charged. And then you work it up with sodium hydroxide, and it basically exchanges to give you ethanol as another byproduct. All right, so the first ethanol came from here, O ethoxide, and this alkoxide here, right, is also ethoxide, right, 2-carbon chain. And so when you work it up with sodium hydroxide, you're going to create ethanol plus water. Okay. So the first step is nucleophilic acyl substitution. The second step is a nucleophilic addition. Okay, just like a reduction step.
Okay.
Both mechanisms involve attack of the pi star CO.
And can we also go over the Arndt-Eistert reaction mechanism? I definitely said it wrong.
Yep, Arndt-Eistert, yep. Maybe 1 second.
Just with the tautomerization part, like, I don't really know.
Yep.
Please.
Yep, so hold on, let me just bring it up. All right, so for this reaction, what we're going to do is we're going to take a carboxylic acid. Okay, first thing we're going to do is we're going to make the acid chloride with thionyl chloride. That mechanism is in the notes from when we did the superleaving group. And so you're going to generate your acid chloride. Then what we're going to do is we're going to do a Wolff rearrangement. And so The Wolf rearrangement kind of looks like this. You take diazomethane, heat it up, and you're going to get this intermediate, which then under heating gives you the ketene. Or I said R, but it really should be acyl. Should be a methyl group, okay? All right, so we should get something that looks like this, where that dot is a carbon atom, okay? The Arndt Eistert is really just attack of that, that ketene with water, right? So we're taking water now, attacking the carbonyl, okay? Electrons move up onto oxygen as a lone pair. And so what do you get? You get a new carbon-oxygen bond. Oxygen now has a negative charge on it there. You can grab the proton, right? That gives us this molecule, or this intermediate, okay? This intermediate, right, then tautomerizes. And remember, for a tautomerization, you get an exchange of a carbon-oxygen, a carbon-carbon double bond for a carbon-oxygen double bond, which is much stronger. And then instead of a oxygen-hydrogen bond, you get a carbon-hydrogen bond, which is much stronger. And so you're going to essentially create now a C double bond OOH. So your hydrogen is going to go here, and your double bond is going to basically move up there, right? So you're exchanging the placement of that that double bond, okay? Right, so this tautomerization is very similar to what we had last semester. Remember when we tautomerized the enol to the keto form? That's exactly what's going on here.
Okay, thank you. That makes more sense.
Right, and so you can do this with any R group right here. So I'll just put in the R group. Doesn't matter what it is. Reaction is the same. Okay, and so this is called the Arndt Eistert because what you're doing is you're essentially saying, I'm going to take this carboxylic acid and I'm going to insert CH2 in between the R group and the carbonyl, right? So this is the new group that forms in between. And you get this because of this combination of first form the acid chloride, then do the nucleophilic substitution, then do the Wolff rearrangement, then do the trap with water, okay? And so it's a specific type of, sequence. Specific type of the Wolff rearrangement that then gets trapped with water.
Okay, thank you. And this type of reaction will always be in this specific sequence, right?
Yep.
Okay. Could we maybe just do like another mechanism example of from one molecule to the next, I guess, and synthesis, I guess, maybe.
I'm running out of examples to help you.
Okay.
Give me a second. I gave you all the problems on the problem set. Well, why don't we try to do this synthesis while I see it. Okay, so I want you to make benzonitrile from these three things. benzene, formaldehyde, and ammonia. Okay. You can only use the benzene, the formaldehyde, and the ammonia as your source of carbon and nitrogen. Right. So what that means is that this benzene ring maps onto this, that carbon atom maps onto that there, and that nitrogen maps onto there. Right. You can use any other type of reaction you want, reagent you want, but it has to have those reagents as the source of those atoms. Okay. All right. So what do we think? What's a good way of making a nitrile? How might we make a nitrile? What would we have to do?
I don't have to just use those molecules, right, for this part?
You have to use these molecules as the source of those atoms in the product structure. But you
Okay.
can use any other reagents that don't appear in the product structure at your will.
Could you do Sandmeyer's reaction?
You could, but that's not going to be using the carbon atom here,
Oh, okay, right.
right? And then that carbon atom gives there, or using that nitrogen to give that nitrogen, right? That's saying you just use sodium cyanide, and that's not what the question's asking. The question's asking just use these reagents as your source of the carbons and nitrogens in your product. Okay? So you have to use those reagents. Right, so what's a different way of making nitriles, making cyanides?
Would you use tosyl chlorine? Tosyl chloride?
Tosyl chloride and pyridine.
Okay,
Okay.
yes.
What would that starting material be? It would be a primary amide, right?
Mhm.
Okay, that's pretty good. We can do a dehydration of that primary amide to give us that nitrile. Now, how could we make this primary amide? What would we do? We probably want to react ammonia somehow. How would we do that? What would our starting material be? I think I can think of two different methods of doing this.
Could you do a Hoffman rearrangement? Or no, just kidding.
Hoffman
With
wouldn't
Gibbs,
give you
yeah.
the correct substitution. Right? Hoffman would give you something that looks
Right.
like this, right? You want something that looks like this, right? So what bond do you need to form? You need to form this bond, right? If you're using ammonia, you need to make that bond. Well, what is that bond? That's an amide bond. How do you make amides?
Is that from last exam? Could you make like an imine or one of those?
What do you want to use?
Could you use R and NO? No, you need NH3. Hold on.
Remember, amides are all the way almost to the left of the reactivity series. So you can make it from anything to the right. Choose a good one to make that amide, right? With the appropriate set of reagents, you could make that amide. I can think of two different ways. Actually, I can think of three.
Could you use acid chloride?
Okay, you could use an acid chloride. Okay, to make that amide directly. Okay, how do you make the acid chloride? What do you start with?
Could you just start with an aldehyde?
You can't start with an aldehyde. Aldehydes don't have 3 bonds to heteroatoms. Acid chlorides have 3 bonds to heteroatoms. So aldehydes are actually a reduced form. Right? Acid chlorides are more highly oxidized. How do you form those acid chlorides?
Something with a superleaving group.
Something with a superleaving group. So there are 2 choices. Which one do you want to use?
Could we use that one again? Tosylate?
Nope.
The
How about that one that I messed up on the exam? Right, thionyl chloride.
okay.
That
Yes,
does the
that
job, or
one.
oxalo chloride. All right, so we're going to use a carboxylic acid and convert it into the acid chloride. Okay, now how can we make that carboxylic acid? Well, we need to have a way of forming a bond in between these 2 things. So the trick here is, what if we were to take that carboxylic acid? How do you make carboxylic acids? You can make carboxylic acids by oxidizing. So what if we were to take chromium trioxide, sulfuric acid, acetone, but start with the alcohol? Why might that help us? It might help us because we can make that primary alcohol from combination of this bromobenzene reacting with magnesium, followed by a carbonyl formaldehyde, followed by trapping with ammonium chloride. And then how do you make that bromobenzene? By simply just taking benzene and reacting with iron tribromide and bromine. Okay. Yeah, I'm just looking through. I think I gave you all the questions I had. Oh, this is a good one. This is not really a, well, it is kind of a mechanism problem, but it's not really one from this last section. So let's say the question is this. Let's say you have this molecule, and for this molecule, there is no peak in the infrared spectra at 1600 to 1700 wave numbers. And you'll recall that this 1600 to 1700 region indicates that you have a carbonyl. Okay. But it does show an absorption at 3000 to 3400 reverse centimeters. Okay. In the NMR, there are no peaks above 150 ppm. But there is a peak at 110. Okay. So what I want you to do is to tell me why this is the case. Obviously, if you don't have a peak in the IR spectrum at 1600 to 1700, that means you don't have a carbonyl. But if you do have a peak at 3000 to 4000, 3000 to 3400, that means you have some sort of OH. okay? But it also tells you that if you have the NMR spectrum, you've got a peak, no peaks above 150. That also tells you that you don't have a carbonyl. But if you have a peak at 110, this is in that overlap region. In that overlap region, we have two things. We have alkynes, but we also have carbons that have that make two bonds to oxygen. So how can we explain this? We can explain this by an equilibrium with the gemdiol. And so we can form a 5-membered ring that looks like this. Or it's not really gemdiol, it's actually a hemiacetal. Okay, and then this carbon would have a signal in the C13 NMR spectrum at 110 because it's bound to two oxygen atoms. It has an OH, and so this is what gives rise to that 3000 to 3400 absorption in the IR spectrum, but it doesn't have a carbonyl anymore. So you're absent any 16 to 1800 or so carbonyl stretch, and you also don't have any really, really far downfield NMR signal. Okay. All right, I'm trying to find you another question. Got nothing. Yeah. I'll have to come up with some others. So right now, nothing's really looking like it's going to be helpful. I gave you that problem set, so that was all the problems I had. Yeah.
Could we maybe just go over workshop 24 then? I don't think I ever got to that in class.
Okay, let me just try one more place.
Yeah, okay.
Why don't we do this one? So I'm going to draw two molecules here. This one here, OCCl3, OCCl3, and phosgene. Okay, so this one is known as phosgene, and this one is known as triphosgene. Right, and triphosgene and phosgene react with nucleophiles, and they react via a nucleophilic ACO substitution mechanism. And I want you to tell me which one is more reactive. Right, more electrophilic. Which one has a lower LUMO? Okay. And then in addition to that, when you react with a nucleophile, when reacting with a nucleophile, which reagent can be used in less than a stoichiometric amount? Less than one equivalent. Okay, so you don't have to add, the reagents, the nucleophile and the electrophile in a 1-to-1 ratio. It might be 1 to less than 1. Okay, so let's tackle this first question first. Which one of these is more electrophilic and why? What do you think?
Would it maybe be the triphosgene?
All right, well, let's first take a step back and try to figure out, well, what determines electrophilicity? What determines electrophilicity?
Well, electronegativity and resonance, maybe, because the oxygens are going to be pulling
Okay,
the electrons
let's take a step back a little bit more. Electrophilicity means where is the delta plus? How delta plus is that carbonyl, right? If it's more delta plus, it's more electrophilic, right? More reactive. And so what determines the delta plus that's on those carbons are things like electronegativity, sigma donation, resonance, inductive effects, etc. All right, so given that, what's going on here? What's going on in the case of phosgene? Does that carbonyl have a lot of electron density on it?
No.
Why not?
Well, you have the carbon-chlorine bonds creating inductive effects.
Okay, that's
And
true. Is inductive effect very strong?
no.
Not very strong. What's
So
the more important factor?
resonance?
Resonance. So can these chlorine lone pairs, can they resonate? Why not?
Well, now I'm thinking about it.
Well, I've drawn it like that, but does that occur? Why not? It does not occur. Why does it not occur?
Would it have something to do with the hybridization of chlorine? Or
Well, they're going to be sp2 hybridized, and so the lone pairs are going to be in an atomic p orbital. You're on the right track. What is it about that atomic p orbital that's different for chlorine?
oh, it doesn't have as good overlap.
Right, there's orbital mismatch. Because there's orbital mismatch, what it means is that resonance is not a factor to increase electron density on the carbonyl. So what do we have left over? What we have left over are inductive effects. So inductive effects predominate. Chlorine is electron withdrawing And so the carbonyl is very delta plus. Let's say delta plus plus. Okay. Now let's go over to triphosgene. What can we say about triphosgene this time?
The oxygen lone pairs will donate.
Okay, oxygen lone pairs can donate, and actually there's two different ways they can donate. And so resonance places negative charge on the carbonyl. Right? So carbonyl is, let's say, only delta plus. Okay? Not as delta plus as the phosgene is. All right? So it's got a higher LUMO. It's less reactive. All right, so this one is less reactive, and this one is more reactive. All right, so this is kind of a logic problem. Right? If this is the case, then what is the consequence? Right? All right, so we've established this question: which one is more electrophilic, more reactive? Okay, the phosgene is more reactive. Now, how about when reacting with a nucleophile, which reagent can be used in less than a stoichiometric amount? So which one of these, triphosgene or phosgene, if it's reacting with a nucleophile, do you not need a full 1-to-1 ratio with the nucleophile? Well, let's take a look at the reaction between triphosgene and a nucleophile. All right, so we've got nucleophile minus, let's just say we attack the carbonyl, we get a tetrahedral intermediate, right, with which now has a new carbon nucleophile bond. We collapse with loss of a leaving group. What's the leaving group this time? The leaving group this time is OCCl3 minus. All right, so we've got new carbon nucleophile bond, OCCl3 plus OCCl3 minus. Let's draw that out. Hey, what does that look like? That looks like a tetrahedral intermediate that can collapse with loss of a good leaving group to give us phosgene plus chloride. And so in the first step here, you're actually generating an equivalent of phosgene. Right, so you've got 2 molecules of phosgene embedded within here. So you really only need 1/3 of the amount of triphosgene to react with all of your nucleophile. Okay? Makes sense?
Yes, thank you. So there's 2 molecules of phosgene embedded, or
Yeah,
right?
so there's
and then
one on the
okay.
one on the left side and one on the right side.
Okay, and then that last like third would be the carbonyl, right?
Right.
Okay.
Okay. All right. So you wanted to do workshop 24. Right.
Yes, please. I think it was just another
Yeah. So
mechanism.
this is actually a little bit of a combination of 2 different mechanisms, both of which you've seen before. So the idea is we have this molecule, CBZ. This is just a protection group for a nitrogen. We've got OH. We've got this primary amide here. And we're going to react this with EDC, with DCC. DCC is an example of a carbodiamide. Sorry, it's not benzene, it's cyclohexyl. Okay, and diisopropyl ethylamine, which I'll just draw out here. Okay, first thing that happens is you're going to take your amine and you're going to deprotonate. Right, so deprotonation of the amine to give you a carboxylate. And so I'm going to do CBZHN, all right, to give us our carboxylate. Right, and then I've got my primary amide. Then my carbodiamide comes along, and we're going to form a oxygen-carbon bond. Right, so we're going to get that oxygen, attack that what looks like a carbonyl, pretty electrophilic. You've got C double bond N on both sides. Electrons move up onto nitrogen as a lone pair. And so what you end up with is, I'll just say here, something that looks like this. R, okay. I've got my nitrogen minus there, cyclohexyl, I'm just going to label it CY, and then this is cyclohexyl as well. Okay, I'm then going to grab a proton from somewhere. I'm going to grab that proton from this diisopropyl ethylamine, which grabbed it in the first place. All right, so I'm going to protonate that species. Right, and that's going to generate my neutral carbodiamide structure. So CY, NHCY. Okay, now how can I form that intermediate that I have drawn as number 2? So let me just draw that in, CBZ, HN. Like this. Okay, this is number 2. Okay, well, what would I have to do? I would have to connect this oxygen atom with that carbonyl. And I need to form a double bonded nitrogen in the first place. All right, so why don't I take my nitrogen lone pairs, move those down, take the electrons from the carbon oxygen double bond, attack the carbonyl, form a tetrahedral intermediate. Okay, so what will that give us? That's going to give us a new oxygen carbon bond like this. Okay, we can transfer a proton around. That's going to give us that neutral species. That neutral species collapses, right, with loss of a leaving group. This time the leaving group is going to be my urea. And so I've got my protonated now form of my number 2, right, plus my urea. So my urea is going to look like this, N minus cyclohexyl, NH cyclohexyl. I can grab that proton off, and then I get to this species. Okay. Now, how do I get to the next species from there? So that next species is number 3, CBZHN, carboxylic acid, and then a nitrile. Well, how do we get that nitrile? What we would have to do is form a carbon-nitrogen triple bond right here. Right, so this is number 3. And then I'd have to break this bond. Just draw it out. I have to break that bond. So we need to form the triple bond and then break the carbon oxygen bond. Well, we can do that with just using diisopropyl ethylamine again, because this is a base. So what we can do is we can do a dehydration, remove that proton, electrons from the nitrogen hydrogen bond move down in to form a carbon nitrogen triple bond. This leaves as a good leaving group, right? O minus, right? And then you simply take that O minus, right? And then grab a proton from the formerly triisopropyl ethylamine. Now it's a triisopropyl ammonium, right? That's going to protonate to give you number 3. Okay. Okay, so this is a peptide coupling, a coupling reagent, followed by a dehydration to give you the nitrile. Okay, make sense?
If there wasn't a base present, you wouldn't be able to get to the third one, right?
That's right.
Okay. Okay, I might be all set for questions for today.
All right, very good. We'll see you
All
in
right.
class tomorrow.
Thank you very much.
Okay, no problem.